If you recall, when taking derivatives of more complicated functions, sometimes we had to use other rules such as product rule, quotient rule, and the chain rule. To find antiderivatives in these situations, we need more advanced methods. In this section, we will learn a method that is usually applied to the antiderivatives when chain rule may have been necessary in finding the derivatives in the first place. So, the U substitution is used to simplify a complicated antiderivative. Even though it works best when finding antiderivatives of a function where the chain rule may have been necessary in the process of taking the derivatives, it can also be used in other situations, usually to simplify the integral. So substituting a new variable u for a function that had been composed with another function, as long as its derivative or a multiple of the derivative is present, lets us simplify the integral to a more manageable form. It's very important for the derivative of the function that we call u to be part of the integral. That will let us replace u and also replace the dx. Otherwise, we won't be able to integrate a function with a variable u which has a dx instead of a du. Well, let's look at some examples. So here we want to find the integral of e to the sine x cosine x. So notice we have a function composition. E is taken to the power of sine x, and we also have the derivative of sine x, which is cosine x, present. So here's an ideal situation for us to simplify this problem using a u substitution. So what we're going to do is replace sine of x with a u. So this part just becomes e to the u. And once again, I do need to get rid of the dx and anything that has an x once I switch my variable. So what we're hoping to do is get rid of the cosine x dx. And as we know, if I take a derivative of sine x, I do get cosine x, so if I take this derivative, I would have du is equal to cosine of x dx, right? So it's just doing an implicit differentiation here. So if I replace all the pieces here now, I am just going to have e to the u, and cosine x dx are replaced with du. And we know that integral of e to the u remains e to the u because the derivative of e to the u is the same. And last thing we always want to make sure we do is replace the u back with the initial function that we had. And in this case, we get e to the sine x plus a c, right? That's our integration constant. Okay, so let's look at a second example. So in this example, we're trying to find the integral of 7x cubed times the square root of x to the fourth plus 7. And once again, notice that 7x cubed is a multiple of x to the fourth plus 7. So if we use u to be x to the fourth plus 7, then we'll be able to use the 7x cubed, or the x cubed part, as the derivative of x to the fourth plus 7. The first thing we're going to do is take the 7 out of the integral, use one of our integration rules to get a nicer integral inside, so the 7's not bothering us, and then go ahead and replace things. So I know u is going to be x to the fourth plus 7, so I'm just going to get square root of u, which is much more manageable. And again, to get rid of the dx and the x cubed, I do need to make sure I pay attention to the derivative of u. That means we get du is equal to 4x cubed dx. And that means x cubed dx is going to be 1/4 du. So going back and replacing these things into my integral, I am going to get 7 square root of u, right? So that's the x to the fourth plus 7 was replaced with the u. The x cubed times dx is replaced with 1/4 du. All right, so next thing I'm going to do is just take the 1/4 out of the integral also. It's a constant. We get 7/4 outside of the integral, and rewriting square root of u as u to the 1/2, so we can apply the power rule for integrals, which means I'm going to add 1 to the power and divide by the result. So I still have the 7/4. I get u to the 1/2 plus 1 divided by 1/2 plus 1 plus the constant of integration plus c. Cleaning this up a little bit, 1/2 plus 1 is 3/2, so I have 7/4 times u to the 3/2 over 3/2. And last thing I need to do is just do a little bit of cleaning up. So divide by 3/2, which means we're going to multiply by the reciprocal, which is 2/3. And combine the two fractions, it can reduce a little bit and replace my u back with its initial expression, right? So 7/4 times 2/3, I can simplify, I get 14 over 12 or 7/6, and the u was replaced with 7/4 plus 7. And maybe finally just put it back in the form we found it, which involved the square root, right? So take the 3/2 and rewrite it as a square root of x to the fourth plus 7 to the third power, plus c. Okay. So one thing we're going to run into are definite integrals. And when we do a u substitution, you got to be a little careful with our limits. There are a couple ways we can evaluate these limits. So one way is to replace things back in terms of x and plugging the original values, or we can bypass that and replace our initial values with the what we get when we plug those into our u function. So a few things in here we want to be careful, right? So since we're plugging numbers in, continuity becomes an issue, and we're going to have to make sure our functions are defined at those values. So here are the things I got to pay attention to. So if g prime is continuous, right? So our derivative function here is continuous on the interval from a to b, so there's no discontinuity. And our function is continuous on the range of g of x in the same interval. Right, so let's make sure we, again, clear why that is. So we're not, the f doesn't have to be continuous necessarily on a to b, but on the range of whatever function g of x we have. So the a's and b's are going to get plugged into my x function. And then whatever the result is, so whatever I get g of x, or basically all the numbers between a and b would get plugged into g. And then the result of that, or the range of that function, gets plugged into the f. So I want to make sure that my function is continuous on the range of g of x between a and b. Well, g prime needs to be continuous on a and b itself. And if those are true, then I can do my substitution, replace g of x with u, and replace my values of a and b with g of a and g of b. So let's look at an example. So here we're trying to integrate 8x over x squared plus 5 dx between 2 and 5. So again, ignoring the 2 and the 5, notice if I take x squared plus 5 and call it u, its derivative would be 2x, and 8x is a multiple of that. So here we have a nice candidate for a u substitution. First thing I'm going to do is take the 8 out of my integral like we did in the previous examples. So we can have a clean slate in there. The coefficients are not bothering me anymore. So I get 1 over x squared plus 5, and I've taken the x and moved it next to the dx. So we can use that when we find our du. right? So I have 1 over x squared plus 5 as my function. X dx is going to contribute to my du. And so as I go ahead and choose my u to be x squared plus 5, I shouldn't pay attention that this is continuous between 2 and 5. Again, it's a polynomial, so it's continuous everywhere. And then if I replace my x squared plus 5 with u, I gotta make sure that the values that I get out of this are not going to have any discontinuities or not create any discontinuities in my function that I end up with, which is 1 over u. Right? So if I go back here and look at what numbers I would get, so if I plug 2 in here, I get 9, so 2 squared plus 5. And if I plug 5 in here, I get 25 plus 5, which is 30. So my function 1 over u, right? So if I replace this with u, I'm going to have 1 over u, would go from 9 to 30. And the function 1 over u is continuous between 9 and 30. The only discontinuity would have been at 0. So if these numbers cause my function to pass through 0, I would need to worry about it. But in this case, there's nothing to prevent me from continuing this. I'm gonna replace, find the du. du is 2x dx, which means x dx is half of du. And I can go ahead and replace the pieces. So I get 1 over u, and x dx becomes 1/2 of du. And I get my limits, the new limits, which are 9 and 30, which is what we got when we plugged in 2 in here and 5. So replacing x with 2, we got 9. Replacing x with 5, we got 30. And the 8 is still the coefficient here. And next thing I'm going to do is take the 1/2 out. And I get 8 times 1/2. And inside I just have 1 over u du, which is easy enough to integrate. So 8 times 1/2 is 4. And then integral 1 over u du, we know from previous section and from our derivative rules, integral of 1 over u du is going to be natural log of u. So I end up with 8 times 1/2 natural log of u. We still got to evaluate that between 9 and 30. So 4 ln of 30 minus ln of 9, right? So those are positive numbers. I don't need the absolute value anymore. And then we can apply a little bit of the simplification rules for logs. Log of 30 minus log of 9, I can combine to natural log of 30 over 9 and reduce that to be a natural log of 10 over 3. So we get 4 natural log of 10 over 3 as our final answer. Now the other option, as I said, would have been for us to replace u at this point back with x squared plus 5. But if we do that, then we got to go back and use the initial limits we had, 2 and 5. The answer would come out to be the same.